Okay, so as I mentioned before, we are going to start working on AP-style practice questions, specifically involving these Taylor and Maclaurin series. Again, remember, a Taylor series is literally a Taylor polynomial, except for the fact that it goes on for forever till n goes to infinity, instead of stopping at the fourth term or the fifth term or something like that. So it says a function f has a Taylor series at about x equals 1. Okay, so that's the center of your series. And converges to f of x for all x in the interval of convergence. So we'll have to think back to intervals of convergence for power series. We know that f of 1 is 1, f prime of 1 is negative a half, and every additional derivative beyond that is based on this formula right here. So obviously if I want the second derivative, I'd plug in n equals 2, third derivative, and so on and so forth, and that would give me the value of f prime, or f, double prime of 1, or triple prime of 1, or something like that. So, part A says write the first 4 non-zero terms and the general term of the Taylor series. So basically I have to write out the first 4 terms that are not 0 and obviously the nth term basically. So remember that for a Taylor series, your Taylor series is based on the linear approximation. So f of a plus f prime of a times x minus a. And then as we go on further, it becomes the second derivative at a all over 2 factorial times x minus a squared, and then the third derivative at a all over 3 factorial times x minus a cubed, and so on and so forth. I'm going to hope that we don't have any 0 terms, but if we do, we'll have to come back. Again, we only want the first 4 terms. So as I've mentioned before, do the general term first, then do the specifics. So the center of our series is 1, so we're going to plug in a equals 1. So f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 all over 2 factorial times x minus 1 squared times f triple prime of 1 all over 3 factorial times x minus 1 cubed. Okay, and again, eventually we'll have to add the nth term for that. So the f nth term of 1 all over n factorial times x minus 1 to the n. Okay, so let's start plugging in some of the specifics. And again, we'll have to use a formula to get the second derivative and the third derivative. So f of 1 came out to be 1. F prime of 1 was told to be negative a half times x minus 1. Okay, now my second derivative, that's going to come from plugging into this formula that I'm highlighting right up here on the top right-hand side. Okay, so the second derivative, f sub 2 of 1, or f double prime, I should say, would be negative 1 squared times 2 minus 1 factorial all over 2 to the second. Okay, so if I clean that up a little bit, negative 1 squared is just going to be positive 1, so I don't have to write anything for that. The denominator obviously will be 4. 2 minus 1 factorial is really 1 factorial, so that's where 1/4 will come from. So we'll have plus. Now remember, that is literally just f double prime of 1. I still have that 2 factorial in the bottom, and then I have x minus 1 squared following that. Okay, so I'll have to clean that up in just a second. Then for f triple prime, I'll do the same thing. Okay, this will be negative 1 now to the third times my n is 3 minus 1 factorial all over 2 to the third power. If I clean that up, obviously that's going to stay negative because negative 1 to the third. 3 minus 1 factorial is 2 factorial, and I'm going to leave that as 2 factorial for a second, and that's all over 8. Okay, so I have negative 2 factorial over 8. Don't forget the 3 factorial that was there to begin with, and then I have the x minus 1 to the third. Okay, and again, eventually I'm going to be able to want to write out what the nth term looks like for that. So I have to clean this up actually a little bit. I know I've said many times you don't have to simplify, but I think this is one of those ones that you're going to want to simplify to be able to try to figure out like what the pattern is in this situation. So actually, let me go back and change one more thing. Instead of making this 4 and 8, let's leave this as 2 squared and 2 cubed, because I think that will help with the pattern when we eventually go to write it out. Okay, so if I have 1 over 2 factorial, 2 squared divided by 2 factorial, I can really write that as 1 over 2 squared times 2 factorial, x minus 1 to the second. Okay, and I'll make this now a negative. Okay, I'm going to bring that 3 factorial up, so I have 2 factorial all over 2 cubed times 3 factorial. So really that comes out to be just, I'll just leave it as 2 factorial, and I'll keep this as 1 factorial. Okay, and then obviously I have x minus 1 cubed. So the reason why I did some of that moving around is because I think it will help us when we start to get to writing the nth term. Okay, so remember, this entire term was based on n equals 2. Okay, notice that you have a factorial that's 1 less than 2. So it's likely that that's going to be n minus 1 factorial on the top. Okay, in the denominator, we always have powers of 2 that also happen to match the n value, right? So this was, again, 2 to the second, 2 to the third. Eventually, we'll have 2 to the n. Okay, we also have 2 factorial, 3 factorial. So eventually, we'll have an n factorial. And then I'll have that x minus 1 raised to the n. Okay, now I can actually go a step further, and maybe I should have done this before I actually got to this point, but you can actually reduce n minus 1 factorial and n factorial. If you remember that n factorial, so I'll write this on the top, is really n times n minus 1 factorial, I can actually cancel this out to be n times n minus 1 factorial. Those factorials will cancel. And so that's how I'll eventually end up with a general term of x minus 1 to the n all over 2 to the n times n. Okay, so here is my Taylor polynomial. Okay, the first 4 terms. And here is my general term for this particular polynomial. Okay, so it says for part B, the Taylor series for f, and you know what, I'm going to move this up. So I'll move this out of the way. Move this up. So it says the Taylor series for f has a radius of convergence of 2. Find the interval of convergence and show the work that leads to your answer. So rather than having to take this expression, so imagine for part B, we have the sum from n equals 0 to infinity, x minus 1 to the n, all over 2 to the n times n. Okay, so again, go back to power series for a second. A Taylor series is a power series. Normally, you would have had to do the ratio test to figure out the radius of convergence, again, with the absolute values and stuff like that. But this question takes away that work of having to do the ratio test and tells you that you have a radius of convergence of 2. So remember that the center of your series was at 1. If I go out 2 units in each direction, then I get a window of x's that I could plug in and end up with a convergent series. So 2 units to the left would be going down to -1, and to the right would be going up to 3. So our possible window of convergence is -1 to 3. But remember, you always have to test the endpoints when we were dealing with something based on the ratio test. So we have to actually plug in the endpoints and see what happens if we actually converge, so we can see if we can underline those values or not. So let me start with x equals -1. Okay, so that would give me sum from n equals 0 to infinity, -1 minus 1 to the n, all over 2 to the n times n. I can clean that up a little bit. That'll be -2 to the n, all over 2 to the n times n. If I clean that up a little bit more, that becomes -1 to the n times 2 to the n, all over 2 to the n times n. So I really am dealing with n equals 0 to infinity of -1 to the n all over n. This one will converge by the alternating series test. So that's telling us at -1 we are convergent, so we would include -1 in our interval of convergence. Okay, then x equals 3. Sum equals n equals 1 to infinity of 3 minus 1 to the n, all over 2 to the n times n. So sum equals n equals 0 to infinity, 2 to the n, all over 2 to the n times n. As I cancel out those 2 to the n's, I end up with the sum from n equals 0 to infinity of 1 over n. And remember, this diverges because it's the harmonic series. Okay, or you could say because it's a p-series with p equals 1. Okay, either way, you're going to find out that we diverge at x equals 3. So our interval of convergence only goes from -1, including -1, up to, but not including 3. Okay, so that's our interval of convergence. Okay, part C. The Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. So basically what we're going to do here is we're going to take the expression we had before. It asks us to use the first 3 terms, and we're going to plug 1.2 into that. Okay, let me add an extra page. Okay, so this is part C. Okay, so let me get rid of some of this highlighting, that extra guy on top. And in fact, let me move that over just a little bit. And so remember, this is basically approximating f of x. And again, they specifically said use the first 3 terms. Okay, so if we want an approximated value of f of 1.2, that would come from 1 minus 1/2 times 1.2 minus 1 plus 1 factorial all over 2 squared times 2 factorial times 1.2 minus 1 squared. Okay, remember, there's no need to actually simplify that. If you did want to simplify or like make a decimal value, you need to keep at least 3 decimal places. But as I've mentioned before, it doesn't need to be simplified. You could leave this as your approximate value for f of 1.2, and I think that would be better than trying to risk making some sort of a mistake as you do your calculation. So now, last but not least, part D. Show that the approximation found in part C is within 0.001 of the exact value of f of 1.2. Okay, they're even kind of highlighting what kind of series this is. So when it comes to error, you're using the alternating series error bound, which again, remember, is like the quote-unquote next term. So remember, if I go back over here, I already had the 4th term. Okay, so I can kind of copy that. Okay, so in part D, my maximum error comes from the next term, if you will. Okay, let me get rid of some of that highlight and whatever extra terms I have. Okay, and then more specifically in this question, because of the fact that I was centered at 1 and I was approximating 1.2, the x that we plug in here is 1.2. Okay, so I can plug that in and I can do the calculation, and you'll see that this comes out to be 1 over 3,000. Okay, that is definitely less than 0.001. So that's how we know that that value of f of 1.2 that we got to be 0.905 is as close to the real value, okay, an error less than 0.001. So it's like 0.906 or 0.904 is the actual real value of f of 1.2 if we had the actual f of x function to plug into. So, as I've said before, I know this is going to get to a point where it gets tricky because we're now starting to get into this world of part 2s. So there's many questions that you're going to start to work through, and I want you to get used to being a little uncomfortable sometimes and not knowing the exact right way to do stuff, but trying to say, okay, I know I can get through part A or part B or part C, and I can do my best on some of those ones that don't necessarily, all come together immediately. It's kind of being uncomfortable that helps us to grow and get ready for these questions, and these are very common AP type questions. So I'm going to ask you guys to try question number 2 for homework tonight. Obviously, over the next couple days, we're going to continue to go over these part 2s and practice them, and then our assessment on Thursday will be based on these part 2s. Okay? Good luck. Obviously, the answer keys are also posted, so you could always be looking up the answers as you go through, but it would really benefit you to try to just do it first and